In this video, we'll be attempting to solve the inner product integral for the first time on a sample signal x of t. We learned earlier that if you have a periodic signal x of t and you want to determine how much energy that signal has at a frequency omega, you use the inner product integral, which I've shown again here. A equals 1 over t times the integral over one period of x of t e to the negative j omega t. So let's go ahead and give that a whirl. We're going to try to solve that for this periodic signal that you see here. So the first thing we're going to need to identify is what is the period of this signal. And the period of the signal is the amount of time it takes for that signal to repeat itself, which in this case is t equals 10 seconds. The next thing we're going to need to know is we're going to need to know what frequency omega to test to see if that frequency has any energy in this signal. So we need to pick a value of omega to test. Now, in theory, we could pick any value of omega we want. We're not constrained at all in what value of omega we choose. And we can certainly try more than one value of omega, and eventually we will. But for today, I want to make a little bit of an educated guess as to what value we're going to use. And that educated guess is going to go like this. Since this signal has a period of 10 seconds, and since we know that in general for a pure cosine that omega is 2 pi over t, I'm going to assume, or I'm going to make, let's say, I'm going to make an educated guess that this signal has some energy at that same frequency because it's periodic at that with that period. So I'm going to make an educated guess that omega equals 2 pi over 10 is a good, there's probably going to be a cosine at that frequency in this signal because this signal has that period. So let's go ahead and try that and see what happens. So let's define the integral. So it's going to be a equals 1 over 10 times the integral from 0 to 10 of x of t e to the negative j 2 pi over 10 t dt. Now, it's not the prettiest thing, but it's going to get simpler pretty quickly. The first thing to notice is that although we're integrating on the interval from 0 to 10, which is one period, you can see that there's actually not a whole lot. Let's say this is 10 seconds right here, so this is 0, this is 10, this is 0. There's actually not a whole lot to integrate, right? So all these regions here between 0 and 3, x of t equals 0, so there's nothing to integrate there. Likewise, all these regions here between t equals 4 and t equals 10, x of t also equals 0, so there's nothing to integrate there. In fact, the only place where there is stuff to integrate is between t equals 3 and t equals 4, where x of t has the value 1. So in other words, this integral will simplify to 1/10 times the integral from 3 to 4 of 1 times e to the minus j 2 pi over 10 t dt. And at this point, we would do well to remember that the integral of e to the at is 1 over a e to the at. And you can see now why this approach, it's so much easier to work with complex exponentials than cosines. If we had worked with complex exponentials, if we had worked with cosines, the first problem is we would have to do one integral to solve for k and a different integral to solve for the phase angle theta. Whereas here we only need to do one integral to solve for a. We get a conjugate for free. And secondly, the actual integrals themselves would be much more complicated. E to the at is pretty easy to integrate. Cosine is complicated because when you integrate it, it turns into sine, and things get a lot harder to solve for. So in this case, our particular value of a is minus j 2 pi over 10. So let's go ahead and work this out. We have 1/10, and then our 1 over a gives us 10 over minus j 2 pi, and then it's e to the minus j 2 pi over 10 t on the limits from 3 to 4. And then, let's see, the 10s cancel, and that leaves us with 1 over minus j2 pi. And then we're going to have a somewhat unpleasant term inside the brackets. It's going to be e to the minus j, 2 pi over 10 times 4, minus e to the minus j, 2 pi over 10 times 3. Alright, and if we want to make our lives a little bit easier, we can just reduce the fractions in those exponents a little bit. We don't need to, but we might as well. Let me just go ahead and do that for compactness sake. That's going to be e to the minus j. Let's see, that'll be 8/10, which is the same as 4/5. So e to the minus j 4/5 pi minus e to the minus j, let's see, that's going to be 6/10, that's 3/5 pi. Now, this is a complex number. It's not written very cleanly, but it's a complex number. So there's a couple ways we could proceed at this point, but in order to evaluate it, probably the easiest thing is just to punch it into our calculator and see what it equals. Now, I'm going to use MATLAB for my calculator, so let's go ahead and give that a shot. Let me pull up MATLAB, and let's go ahead and type in the value of A and see what we get. So we have A equals, and let me get the parentheses right, it's going to be e to the minus j times 4 times pi over 5 minus e to the minus j times 3 times pi over 5, and that's all going to get divided by minus j times 2 times pi. And then if I want to see what the values are, I can just say display the, well actually let's just do this. Let's run that. So now you can see that A is in memory, and A is a complex value. It has a real part and an imaginary part. But for us, we want to display the magnitude and the phase. So in order to do that, we're going to tell MATLAB display the magnitude of A, which is the ABS, absolute value function, and we're going to say display the angle of A. That gives us the phase angle in radians. So we evaluate that and we get the following. So let's go ahead and put that back in our code and in our notes and see where that gets us. Here's our results. Okay, so let's just make that font a little bigger so that everybody can read it. Okay, so let's examine what this means. So we've solved for our value of A, and it's got a magnitude and a phase. So what I think this means is that our complex number A equals 0.0984 e to the minus j 2.1991, which, as you recall, equals k over 2 e to the j theta. So putting all this together, what this tells us is that this cosine, which I'm going to call c sub 1 for cosine sub 1, is going to equal, let's see, k. If you want to know the value of k, you take the absolute value of A, which is k, will give you k over 2, and then you double it, that gives you k. So it's 2 times the absolute value of A times cosine of, the frequency of the cosine we're dealing with is 2 pi over 10 t plus the phase angle of A. Let's do it like this, plus the phase angle of A. Okay? Which in our case, 0.0908, let's just say that's 0.1, so this is about equal to 0.2 cosine of 2 pi over 10 t plus, minus 2.1991 radians. Okay? So, last thing I'm going to do is I'm going to go ahead and plot this. So back again to MATLAB, I want to see whether or not this cosine has any bearing on the actual plot that we're working with. So what I've done here is I've gone ahead and I've pre-typed all this out. So this is me defining the square wave. So if I just evaluate that real quick, you'll see let me just plot that, plot t comma x. So there's our square wave. You can see it's periodic with 10 seconds, and then it goes up between t equals 3 and t equals 4. And then here's our cosine. So we're working with a cosine with this frequency. Here is our value of a typed out again. And then I've said that k is twice the absolute value of a, and p is the phase angle of a. And then finally, c1 is the cosine, k cosine omega t plus phase. So a word about good coding technique, you'll notice that once I type in the value of a, I don't bother with actually typing in the numerical value of k over here on line 8. I mean, I know that the value is about 0.2, but why round it? Why bother typing it in by hand? Just let the computer handle that detail for you. If I say 2 times the absolute value of a, then the computer will know the exact precise value of k. So let's go ahead and plot this, and you can see our cosine superimposed now with the original signal that we're trying to work with, and it's pretty cool, right? There's some neat things you can see. I think the first neat thing to see is that without really even meaning to, our cosine that we generated lines up perfectly with the square wave. So you can see the square wave goes up between 3 and 4, and our cosine peaks right in the middle at 3.5. Okay, and it does so at exactly the same frequency as the square wave. So it looks like we're off to a good start. In subsequent videos, we will start to add more cosines into this. So we'll start to query this same square wave and see, is there energy at other frequencies as well.